Yes.
These are all simple methods. They are not difficult methods. Castigliano's second theorem. As we did one problem, right? All other problems are also linked like that. They are simple methods. To find a slope, you have to apply moment, fictitious moment. To find a deflection, you have to apply fictitious force. Just 2 or 3 examples you practice, you will get an idea how to do. Castigliano's theorem and strain energy method, work energy method. Generally, they will ask in this either problem on Castigliano's theorem or the unit load method. All right. So we'll do problem on the unit load method. This is also one of the subsets of the principle of virtual work. We won't go into the detailed proof of it. There is a proof in given in textbooks. Oh, what's happening? Just a second. Now, I'll just explain the method, and then you can we will apply for a particular beam. Now, let's say we have a beam, some beam, be it continuous or simply supported, propped cantilever, doesn't matter what the beam is. Now, it has some issue. This has. Okay. Now let's say there are many loads acting on the beam. Say P1, P2, P3, P4. And just a second. So these are loads acting on the beam. But I need deflection at some other point. Let's say this is point A, this is point B. These are points, some other point, but I need deflection at the point C. So what do I do? Now, in the principle of virtual work or this unit load method, we add a fictitious or the dummy load. This is not the actual load. This is the dummy load. This is the unit load. In the principle of virtual work, we will take this as some P, and later we'll assign P equal to 1. But this is a dummy load. So now what we do is treat this like this. So we will treat this at the point that we need the deflection. So we want to find deflection delta. So at the point we need deflection, we'll first apply the dummy load. Now this will give some deflection, say delta 1 or delta C. This is not important for us. Then we superpose, keeping this load intact, then I add on. It is not that it is a superposition. I add on various loads. So this load is intact here. Then I have the various other loads. So now when I add these other loads, now this is the dummy load, unit load. Now what happens? The deflection, you see that. Oh, I'm sorry. Control. I'm sorry, there is some issue with the pen. Go all over again. I'll just use a single color. When I'm trying to change the color, there is some issue. I'm doing from home. Okay. I'll explain this again. So at point C, I want to find the deflection. So I apply a unit load here. Okay. Now this unit load, just due to this unit load, I will get a deflection, say delta C. Now after this, although these loads are acting first and I am introducing the unit load later, but we will analyze as if the unit load is acting first and then these other loads. So now what happens? Let's see the deflected shape. Now, due to the other loads, this deflection, very important, this deflection is delta. This deflection is delta. So, according to the work energy principle, work done by external forces is equal to the internal strain energy stored due to deformation. Now, you will get this work done, a lot of calculations you will get. I'm skipping those calculations. But now, first we apply unit load gradually and it produces this deflection. Now we are interested after this stage, when loads P1, P2, P3, P4 are added, what happens is you get this new deflection delta. Now the work done by this unit force. So work done by the unit load in moving by displacement delta. Okay. Why is this delta happening? Because of these forces. Now is equal to the internal strain energy stored due to the action of the applied forces. So this becomes 1 into delta is equal to just a second. This is 1 into delta now this for bending. Of course, this principle of virtual work for axial loading is different, for bending it is different, for shear it is different. Okay, but when we talk about bending, this turns out to be like this. This turns out to be integral 0 to L small m capital M by EI square, no, EI small m capital M by EI dx, where small m is bending moment at a section X due to unit load or virtual load. Now this load can be a force, it can be a moment, and capital M is the bending moment at a section X due to real loads. So we just need to apply this particular equation. Del 1 into delta is equal to integral 0 to L small m capital M by EI dx. So just by application of this, we will be able to solve for the problem. How you derive this is a little involved process. We will not get involved into it. There is, you can just refer to the textbook, you will get. We will take a simple example, Castigliano's theorem. We did this problem of a cantilever with a point load at the end, and we want to find the deflections at the end and deflections at the slope at this particular end. So let us do the same problem by unit load method. Okay, there is on this example, we'll do a simply supported beam first and find by unit load using unit load method or virtual work principle. Find the deflection at the free end of the cantilever shown. So let this cantilever be now let this cantilever have a UDL. Now for this cantilever, we know what is the deflection at B, delta. We know what is it? W L cube by 6 EI. No, that is the slope theta. And delta B is W L power 4 by 8 EI. We know this, we want to find. So solution using principle of virtual work or using unit load method. Apply a unit load 1 kilonewton at the end B. Okay. Then let the beam be loaded by moment by load W kilonewton per meter. Now bending moment diagram due to unit load. Now if there is a just unit load is applied, so we are finding M. So bending moment diagram for if there's a just a unit load, the bending moment diagram will be a straight line. This is L. So 1 times L. 1 times L, you will get L here, L kilonewton per meter. Okay. Now at any point X, at a distance of X, now this will be small m. Small m will be 1 times L minus X, kilonewton meter. This will be the moment, bending moment at some point X. Then bending moment due to applied load or real load. Due to the real load, the bending moment diagram, it is a UDL. It will be a parabola. So it will be WL square by 2 at the end. But here, at any point X, mx is what? How do you calculate at any point X? At this point, due to this load W, W into L minus X into L minus X by 2. WL minus X whole square by 2. Of course, both these bending moments are negative, by the way. Both of them are negative. Now, by the virtual work principle, one times delta B, work done by the unit load, is equal to integral 0 to L M capital M by EI dx. So we have integral 0 to L. Small m is minus of L minus X. Capital M is minus W by 2 into L minus X whole cube upon EI. So minus minus becomes plus. You have W upon 2 EI into integral 0 to L minus X the whole power. So this is square, I'm sorry. L minus X the whole cube. So integral of this is L minus X whole power 4 by minus 4. Apply load 0 to L. So W by 2 EI by minus 4, you get 0 minus L power 4. So we get delta B as W L power 4 by 8 EI. This was the result. What did we do? Small m is due to the virtual load or the unit load. Capital M is moment due to the actually externally applied loads. So M by EI. If you do directly, you will get this result. So you have seen W L power 4 by 8 EI and you are getting WL power 4 by 8 EI. Okay. This is finding the deflection. Now to find a slope at B, To find slope at B, use a moment of 1 kilonewton meter at B as the unit load or virtual load or virtual. Now remember, when we say load or load, it can mean force or it can mean moment. Okay, the load can be a force or a moment. And when we say a virtual force, it is meaning both force and moment. So I want to find a slope at B. For which problem? For the problem of the same problem, beam with UDL. The same beam with UDL. But then now I need to use a virtual moment. In Castigliano's theorem, we used a fictitious moment m, but here we will use a unit moment. So this is your virtual load, virtual force. So now I want to find theta. So I have to use 1 into theta. 1 is the moment. M into theta will be the energy. Just like the work done is 1 into delta. So here moment into theta. This is what we need to find. This will be equal to integral 0 to L m capital M by EI dx. Now what will be the small m? Small m here will be a different entity. Small m will be bending moment at any section x due to this virtual load. At B. So the bending moment will be a constant and it will be a Hawking bending moment of 1 kilonewton meter. Now this capital M is bending moment due to the actually applied load, which is same as the previous case. What is it? Capital M is minus W L minus X the whole square upon 2. So therefore, by the principle of virtual work, by the principle of virtual work, 1 times theta is equal to integral 0 to L small m capital M by EI dx. Small m is minus 1. Capital M is minus W L minus X the whole square by 2 dx. This is W by 2 EI integral 0 to L minus X the whole square dx. So we get W by 2 EI L minus x whole cube upon 3 divided by a minus 1. So we get 0, substitute limits, and we get L cube. Therefore, theta B is WL cube by 6 EI. We solved it. Slope. So to find slope, I introduced a virtual moment of 1 kilonewton per meter. To find the displacement at B, I used I'll draw here. I used a virtual load. Okay. Deflection, I use force. To find slope, I use moment. And same result. Let us do another example. Question 2. Okay, we can do this. Okay, find the slope and deflection for the following beam. At the free end. The beam A, B now the load is a triangular load. Load is triangular load. It is 18 kilonewton per meter here, and it is 0 at B. And the length of this beam is 3 meters. And given EI is equal to 40,000 kilonewton meter square. So solution. First, finding deflection or finding slope. Finding slope. So this is first part. Introduce a virtual moment 1 kilonewton at B. So at any point x, from the end A. The bending moment here, small mx, will be the same. Now, due to the load, the bending moment, so how do you calculate the bending moment? This is the real load or the externally applied load. Now at this section X, the bending moment calculation will be like this. Sum of all the moments due to forces acting on the right. So on the right, the bending moment, the load that is acting is half base into height. This is X. This will be L minus X. So half base. Now what is height? Now this is total length is 3. So this is 3 minus X. Now for X equal to 0, W is 18. And for X equal to 3, W is 0. So how does W vary for X equal to X? So we get W minus 18 is equal to the slope 18 minus 0 by 3 minus 0 minus 3 times X minus 0. So we get 18 minus 6X. So we get W as 18 minus 6X, which is true when X equal to 0, it is 18. When X equal to 3, it is 0. So the height at this point, any point X, is 18 minus 6X. So half base into height. Height is, so you pull out 6. No, this is the load multiplied by 2 by 3 times, no, 1 by 3 times, because I have to take moment at this point, and the centroidal axis will be this. So it is 1 by 3 times the length, 3 minus X. So you pull out 6 common. You get 3 minus X, 3 minus X, 3 minus X. So 3 minus X, the whole cube, with of course a negative sign. This is mx at this point, minus of 3 minus X, the whole cube. All right. So now by unit load method, or by the principle of virtual work, one times theta b is equal to integral 0 to 3 small m capital M by EI dx. Integral 0 to 3 small m is -1. Capital M is minus of 3 minus x, the whole cube. So you get 1 by EI. So we get numerator, we get 0 minus 3 power 4 by minus 4 EI. So theta B is 81 upon 4 times 40,000. Okay, because all things are in kilonewton meter, so this also in kilonewton meter square, so everything is Newton meter. So we have to do 81 divided by 8. No, divided by 16. .062 10 to the power minus 4 is the slope. This is the slope. Now finding deflections. This part remains same. Only this part remains different for this part becomes different for deflection. Finding deflection. At B. Introduce a virtual force so small mx will be 1 times L minus x L is 3, so 1 times 3 minus x with a negative sign. Therefore now by the principle of virtual work, by the principle of virtual work, 1 times displacement delta B or capital delta B, this is equal to integral 0 to L 3 small m capital M by EI dx. Now small m is minus of 3 minus x. Capital M is minus of 3 minus x the whole square, no, whole cube. Upon EI. So this is 3 minus x the whole cube. So 3 minus x whole power 4, 3 minus x whole power 5 upon 5. So 3 power 5 is 243 into 5 into 40,000. This calculation will be 243 divided by, just a second, 243 divided by 5 fours 20. 12.15 into 10 to the power minus 4 meter. In mm, it will become 1.215 mm. So this is the answer. So whole crux lies in small m, capital M. Small m is due to the virtual load, finding the moment at a point. Capital M is due to the externally applied force. And solve the problem using this integral 0 to L small m capital M by EI. Okay, this is a very simple method. Now let us do this example just for a simply supported beam. Are you all understanding? I'm giving examples, so one after another you practice, you will get it. For a simply supported beam, with UDL over the entire span, find the maximum deflection at the midspan. Now we know that it is 5 WL power 4 by 384 EI. So this midspan. But what do? We apply so what do we do? Apply uh, just apply virtual load one kilonewton at point C. Now due to the virtual load 1 at this point, the bending moment diagram small m, the bending moment diagram will be this: A, B, C, W, L. Okay, this is L. So W L by 4. So I'll get W as 1. So I get L by 4 kilonewton meter. This point. Here the bending moment is W by 2, that is 1 by 2 times X. And here in this section, the bending moment is W by 2, 1 by 2 into L minus X. So Mx has two parts here. It is W by 2 is 1 by 2 times X for X lying between 0 to L by 2. And this is half of L minus X for X lying between L by 2 to L. So this is the two-part function here. Now, the bending moment due to bending moment due to applied load at any section X. Now, due to applied load at any section X you take, we get W L by 2 into X minus W X square by 2. So, by the principle of virtual work now, by the principle of virtual work, 1 times delta or delta C 0 to L, integral 0 to L, what you get is small m capital M by EI dx. This we will have to split as 0 to L by 2. Small m 0 to L by 2 is half x into half L minus x by EI. Now, from L by 2 to L, this will be half, instead of half x, it will be half L minus x. Oh, I'm sorry. This is half small m into now this is half times L minus x into this. So now let us integrate. If you take W x by 2 outside, you will get W x square. You can just multiply by x throughout. So 1 by 4 integral 0 to L by 2 1 by 4 EI 1 by 4 EI into WL by 2 x square WX cube by 2. not 2. That 4 has come outside already, so this 2 will not be there. Or I'll keep this 2 here and 2 as it is. I've just taken x inside, that's all. Okay, we have to evaluate these two integrals. Now let us evaluate this. 2 common, so 1 by 4 EI into W L x cubed by 3 minus W x power 4 by 4, 0 to L by 2 plus 1 by, 1 by 4 EI into integral L by 2 to L. This is L minus x into x. So x into L minus x whole square. So x L square minus 2L x square plus x cube. This is WL into L cube by 8 3s 24 minus WL power 4 by 16 4s 64 plus this will be L square x square by 2 minus 2L x cube by 3 plus x power 4 by 4. W out. Now let's calculate this. So this is W 1 by 4 EI into W L power 4 by 8 if we take out 8 threes, 8 eights. Now let us substitute. This is L power 4 by 2 minus 2 by 3 L power 4 plus L power 4 by 4 minus L power 4 by substitute L by 2, L power 4 by 8 minus of minus plus 2 you will get 8 L cube by 8, so L power 4 by 12 minus L power 4 by 16 4 64. Nothing is cancelling. Okay, WL power 4 by 32 EI into 5 upon 24 plus this we will do what can be the LCM. 128, no, 12 and 64, 64 threes, no, just a second. Okay, I'll do a rough calculation here. Let us do a calculation. 1 by 2.5 minus 2 divided by 3 plus 0.25 minus 0.125 plus 1 upon 12 plus
Excuse me, sir.
yes.
Sorry to interrupt, but Swapna ma'am is waiting. She has a class, it seems, at 3:15.
Okay, all right, so you can log off. You all can log off. Okay, I'll just complete this and give to you. You can take this. All right,
Okay, sir. Thank you, sir.
thank you. So we get delta B is 5 WL power 4 by 384 EI, which is the standard result. Okay, so here we end. Okay, I'm ending the meeting.
Thank you, sir.